Good morning, everybody. Happy to see you at this early hour, and welcome to our workshop entitled Improving Data Analysis for Ambient Ionization and Direct Infusion MS-based Metabolomics. It's quite a title and quite a content for a Monday morning, but I hope that we will all be able to teach you something about this interesting topic. For today's workshop, we have three presenters. We will head off with Dr. Nick Birse from Queen's University Belfast, who has a long-standing experience in the application of a number of ambient ionization and direct infusion techniques, and he will give you an overview of all the existing techniques and their, let's say, pros and cons and pitfalls. And then afterwards, we will continue with the other presenters that I will introduce when it's their turn. And in the end of the workshop, we will have, for another, let's say, 15 minutes, a Q&A session where we will answer any question you might have for any of the presentations that you've seen so far during the workshop. If in between the presentations you have early questions, you're also welcome to already ask them, but if possible, we would prefer to address them simultaneously at the end. So that's for the introduction. So Nick, the floor is yours.
Right, let's get this presentation loaded. It's a preview. Mm-hmm. Okay, good morning, everybody. Thank you for making the effort to come at such an early hour. I apologise for... what is this doing? Right. So I apologise for blinding you with my slide deck, but we'll crack on with this. So I'm going to give you an overview of the techniques that exist and introduce you to some of the issues that are likely to arise or that you need to think about when doing mass spectrometry with ambient ionization or direct infusion techniques. So we'll cover a bit of the background, and we're going to focus mainly on what ambient ionization mass spectrometry is. Also cover a little bit about direct infusion, because most of you will be familiar with what the fundamentals of direct infusion are, and quite a lot of you will have done direct infusion in some way, shape or form, perhaps not realizing it. I'll talk about some of the source technologies and their usage that exist, and the types of samples that you can use, and the types of data, and the general benefits that you're going to get from going with either an ambient or direct infusion approach. I'll cover what's available from some of the key vendors that's available as an OEM package, and talk about the sort of support that's available from those vendors. And we'll also touch a little bit on some of the homemade witch's brew type stuff that exists that you might come across in publications. As you'll discover, ambient ionization in particular is very well suited for people that like to tinker about and manufacture their own sort of sources. We'll cover some of the different types of analysis, some of the different ways that you can go around generating data. And then we'll talk about some of the future applications, a combination of what we know is coming from vendors, or what we would like to see in terms of vendor support as we progress into ambient becoming much more mainstream. So the first thing is, what is ambient ionization? And there's a realization that for those of us that do ambient ionization, we know really quite a lot about it, but for people that are used to doing LCMS or GCMS based metabolomics, lipidomic studies, or targeted analysis, might not really know much about ambient at all. So we'll just start by introducing what it is. So ambient is where the sample is introduced into the instrument under atmospheric pressure or a very minimal level of vacuum. So you don't have this high vacuum condition that would normally exist in a conventional LC or GCMS system. It also allows either simplified sample preparation or the elimination of sample preparation entirely. So you can get away with taking a tissue sample, for instance, and introducing it directly into the mass spec without having to go through extractions, catchers, cleanups, those types of conventional sample preparation. And ambient ionization sources tend to be instrument agnostic. There's no one source that's highly specific to a vendor. It's possible to do most types of ambient ionization with most vendor instruments. Though there are, as we will come across shortly, some patent and some sales restrictions that tend to lock certain techniques a little bit more closely with some vendors. But there's nothing in terms of the actual design of the instrument that tends to restrict ambient to one vendor. So the commercial sources that you may have seen in publications, and these are just some of them, there are other sources available on the market, and we'll cover them on successive slides. But there's DESI, which is desorption electrospray ionization, and that was developed by Graham Cooks's team over in Purdue and brought to market through their spin-out Prosolia. Intellectual property for that was subsequently bought by Waters, and the Prosolia IP is now available as the Waters DESI source, which is available for Waters QTOF instruments, and as of ASMS last year, it's also available on their triple quadrupole TQ Absolute instrument. And I can say from experience that makes a particularly nice combination. ASAP, atmospheric sampling at ambient pressure. There's a couple of slight variations on what ASAP means, but that's the typically accepted one. That was sort of picked up. It's been developed by 2 or 3 different companies. IonSense do an ASAP probe, but mainly Waters have picked that up. And a few years back, about a decade ago, they released it as an ASAP probe for their Xevo instruments. Fits in, replaces the probe in their standard Z-spray ESI source. Has now since come to market in the last 3 or so years as the Radian ASAP, which is their single quadrupole instrument, and makes a really nice, rapid unit resolution screening instrument, sort of step beyond spectroscopy as a nice screening instrument. Secret's a relatively new technique. It's a dielectric barrier discharge plasma technique, which has been commercialized by a company called Plasmion. That's made it to market on a more formal basis in recent years, although dielectric barrier discharge has been around for quite a while. Agilent have a marketing agreement with Plasmion for food and environmental, and Waters now have a marketing agreement as well with Plasmion for clinical applications. It's available on everything from the single quadrupole Agilent IQ, Waters QDA, through to the Waters cyclic iMobility system. So it's a very, very widely available source. And then finally there's DART, direct analysis in real time. Again, it's a plasma source, but this has a bit more heat and a bit more electronic potential to it. And IonSense brought it to market. Sort of started off with GEOL. IonSense then sort of spun out. They did a partnership with Waters. And then there was the DART QDA or QDA DART system. Again, a single quadrupole system, and Bruker bought out IonSense in 2022, and there's some developments that I'll talk about when I go through the vendor-specific section, where Bruker have now integrated the DART source onto a triple quadrupole instrument really quite nicely. As I said, homemade tech, there are people that are taking either some of the technology off the shelf, so there's people that have got things like the secret source and have added that into Bruker Maldi, or have added on parts to other existing sources to provide secondary ionization mechanisms. Additionally, there's with ambient sources, there's a variety of different sample introductions and additional ionization mechanisms. So, laser systems and such make it a particularly good way of getting a sample volatilized and then perhaps partially ionized into a stream of gaseous molecule that can then be taken up through the source itself, ionized, and brought into the mass spectrometer. The other thing that ambient mass spectrometry benefits from is that the sources tend to be, in mass spectrometry terms, relatively inexpensive, so they're well suited to being used in homemade applications or adding one or more ambient techniques together to do multiple different types of ionization in succession. The techniques also benefit from being able to handle a wide variety of different samples. So techniques such as REAMS can cope with tissue samples. So REAMS, rapid evaporative ionization mass spectrometry, started life as a way of analysing the smoke that's produced from an electrosurgical knife in cancer surgery. Developed by Zoltan Takats, who's another alumni from Graham Cooks's lab. Developed that to see if it was possible to identify biomarkers for cancer, and they could then identify the margin between healthy tissue and cancerous tissue as the surgeon was cutting the tissue sample. It means that you can simply take a tissue sample, whether it's a cancer biopsy or whether it's, in the case of stuff that I've done a lot of, meat samples, beef, chicken, horse, those sorts of things. With a electrosurgical knife, a diathermy instrument of some description, it generates smoke, and you can even use something as simple as a soldering iron. It doesn't have to be anything quite as sophisticated as a surgical knife. That generates that smoke plume, which is then introduced into the instrument, and that's brought into the instrument largely by the instrument's own vacuum. It's not even necessary to include an additional vacuum system or anything. So again, that simplifies the introduction process. DART as well, there's some 45-degree ablation attachments for the DART source, so you can put a piece of tissue or a sample, something like a pharmaceutical tablet if you're interested in an unknown pharmaceutical product. You can get the DART source to sit at a 45-degree angle. The plasma ablates over the surface of the specimen and is then taken into the instrument. DART sources tend to have a small little additional vacuum pump, a little diaphragm pump, but again, it's an inexpensive thing compared with a standard sort of roughing pump that you would find on a mass spectrometer. Liquid samples, extracts, reaction monitoring, DART, again, you can put liquid samples through. You can either allow the liquid to, or solvent to evaporate off, leaving your analyte of interest, or you can spot and introduce, playing with the microphone, you can either introduce the sample still in a liquid form. DESI is very good, desorption electrospray ionization. You can spot samples on there. People might be more familiar with DESI for doing imaging applications where you take a tissue sample, but you can also plate up multiple extracts on a plate and analyze those one after the other in sequence. And then ASAP. Most sample introduction on ASAP is done using a glass capillary. There is recently, should have been announced at ASMS, there's also some new Kevlar swab technology for ASAP as well, which will aid in its use in law enforcement sort of applications looking for narcotics and explosive residues. Then there's also gases, whether it's breath analysis, volatiles, Secret's particularly good for that, and that has a dedicated breath analysis module, and that obviously deals with some of the issues around breath analysis where you've got condensation coming out from your breath. Dart can also be used, and particularly very good for volatile analysis, and it has an online reaction monitoring option for the Dart that can be used. One of the real benefits of ambient ionization is that it tends to be a less energetic ionization technique, so you tend to get more parent molecular ions rather than getting a lot of fragmentation. So if you're used to doing GC and electron impact and you're working out your fragmentation pattern and working backwards, what you'll find with ambient ionization in particular is that you tend to get a lot of M plus H, M minus H type ions. That's not to say it's not possible to do fragmentation. You retain, for most of the instruments that we do ambient ionization on, you retain control of things like your cone voltage or your fragmenter voltage. So you can ramp up to enhanced ionization. You can still tune most of the instruments in the way that you would tune a conventional ESI-based instrument. And you can do in-source fragmentation in the same way that you would do that with an ESI source. So that's a quick background of what is ambient ionization. What we also want to now look at is what's direct infusion. So, as I say, most of you will be familiar with that because direct infusion, also known as direct injection mass spectrometry, is making use typically of the standard ESI or APCI type sources, multi-mode source, those sorts of things. But it can either remove or reduce the LC, or less typically with the GC component, and gets a sample straight from an extract from a vial into the instrument without having to go through a chromatography column and without having to have all of the time-consuming option of setting up the correct column, doing a lot of method development, and can get an answer as to what's in a sample in a few seconds rather than minutes or longer that would take if you were going to do a conventional LCMS run. Now, the system, or the vendor, in fact, that has the most useful setup for that is Waters. They have the IntelliStart option on the front of their instruments where you've got, depending on whether it's triple quad or a time-of-flight instrument, you've got your calibration solution, reference mass solution, and then there's the option to put in a sample in front of the instrument. Most people, if they've used that, will have done that to tune a specific compound and get everything set up for going on to then do LCMS. But it's possible to just stop after you start injecting samples through the IntelliStart system. The downside of that is it's quite low throughput. There's a lot of purging of the fluidic system. If you're familiar with Waters, it can be quite a slow, laborious process. One of the other options, if you've got something maybe like an Agilent system, syringe pumps are available. Get your sample into a syringe and then just inject it at a steady, maybe a microliter or 2 microliters per minute, depending on the concentration, depending on your instrument sensitivity, and start to observe what's coming through your system. Both of these types of sources are methods of introduction are ideal for individual samples, small numbers of samples. But if you want to do very high throughput, and that's kind of the purpose for what we're talking about here, you probably actually want to go back to an LCMS system. And the easiest way to do direct injection is to take something like an auto sampler, and the Agilent 1290 here is ideal for this because it supports both vials and 96 well plates in the same configuration. Also supports 384 well plates, which is even better for higher throughput. And this can be a quick way of just injecting sample after sample after sample every few seconds, and you can inject based on the sample loop that you have installed in the auto sampler. You can go up to maybe something like 25 microliters, typically with a pretty standard 1290. But you're going to set your injection volume again based on the sort of sensitivity and the concentration of your sample that you're interested in. The benefit of going back to using an LC system but without doing conventional actual LC is you don't have to worry about column selection. You don't necessarily have to worry about getting the gradient correct and worrying about getting good separation. And you can also put, by including a little bit of solvent from a chromatography pump, from a binary or a quaternary pump, for instance, you can put in some of the ionization promoters, so you can pop in a little bit of formic acid, acetic acid, those types of things. Or you can start thinking about putting in some sort of dopant or promoting adduct formation to get a little bit of differential adduct formation that can give you a little bit of separation that you might want to use to get a little bit of additional separation without going to all the trouble of doing chromatography. So if you've only got a small number of analytes that you're interested in, there's maybe just two that are maybe starting to be difficult to separate just with the instrument itself, but you get differential adduct formation. That's a perfect way of dealing with that sort of problem. Direct injection or direct infusion is ideal because it's all very familiar. You've got the same source options. Potentially there's no requirement to buy anything for your system. At most you might need a union to connect one side of the column oven to the other to account for the fact that there's no column in place. So you can get away with a very, very low cost modification of your existing instrumentation. There's no need to reconfigure the instrument. You've got the same source options. Unlike maybe moving between, say, a Reams system and ESI system, which requires the instrument to be vented, to go between doing conventional LCMS, ESI, and direct injection, ESI, you don't have to do anything to the mass spec at all. There's no venting. There'll be maybe just some small configuration changes in the software, nothing of any real consequence, which makes it very easy to switch between maybe doing direct injection, running through maybe 1,000 samples over the course of a day or a couple of days. And then when you've got a list of samples that you want to focus in more detail, change the software settings and then maybe focus on the 20 or 30 samples that you're most interested in, and you can go back to doing your LCMS analysis on them. The benefit of direct injection is you've got the same ionization mechanism, so you can start to understand that you've got the same source conditions, you've got the same in-source fragmentation issues, those types of things occurring. So there's nothing mysterious going on there. So it can make understanding the data a little bit easier. So, as I say, going OEM, so this is what's available from vendors, and it's not an exhaustive list. There's probably something that I've missed because I didn't make it to ASMS, and there's probably something that was released 2 weeks ago that's not on the list. But it's sort of typical for what's out here. So Waters, they've embraced ambient mass spectrometry more than most other vendors. So on the market at the moment, they currently have the ASAP system, the Radian ASAP. First demonstrated, as I said earlier, with the Xevo family, and you can get the ASAP probe if you want to do ASAP with cyclic or an MRT or something. You can do ASAP on that. But where they've really developed over the last 2 or 3 years is with the single quadrupole Radian ASAP instrument, and it's an ideal screening instrument, really, really nice. You've got that molecular weight specificity that can really start to tell you if you've got a problem with a sample very, very quickly. Very, very cheap in terms of an instrument, and the single quad QDA is a very, very robust instrument, tends to stay quite clean, doesn't have too much of an issue with the instrument having to be stripped apart and cleaned from source to detector. So it's a nice starting point. There's DESI, which tends to come at the other end of the spectrum and works really, really well on the high-end instruments. Really works incredibly well on things like the ionizability, the MRT, and the Synapt instruments for DESI imaging applications, and you get some very, very tight spatial resolution for DESI imaging. As I said before, it was released on the triple quadrupole TQ Absolute, so you can do targeted DESI imaging, and that is a phenomenal setup. The sensitivity that you can now get with that is really, really impressive. So if you're looking for specific metabolites, even at very, very low concentrations in tissue samples, it's wonderful. They do reams. It's a little bit niche, but it has a big potential to do some GCFID killer work in lipid analysis. If anybody was at ASMS, one of the students that I co-supervise presented on doing double bond positioning using reams. So we're still developing the applications in terms of lipid analysis. Lynn's group from Ghent are doing an awful lot of work on laser ablation reams as well. So there's a lot of work in the academic sphere to just keep on improving reams. And then there's DART QDA. It's sort of drifted away now that IonSense was bought out by Bruker, and DART sort of sits now more with Bruker, but people might well have a DART QDA system or be aware of it, so I'm just mentioning it here. The sort of use of DART has kind of been supplemented by ASAP on the single quadrupole family. But it does exist, so I'm just making you aware of it if you see it in the field, or you end up in a lab and you see a little single quad with a big blue source sticking out the front. It's there. Waters are still supporting it as well for a few years post-Bruker takeover. Which brings me on to Bruker. And over the last couple of years after they bought out IonSense, they've done what those of us that have been doing ambient mass spectrometry for years and years and years have been begging people to do. They've properly integrated an ambient ionization source into an instrument. So whereas with things like the DART QDA, you have a separate bit of software to control the DART source, and then you've got the MassLink software to control the QDA mass spectrometer. With Bruker, they now have an integrated solution where everything is controlled from the same software. And they brought that to market as the EvoQ DART TQ+. Bruker have also done some investments in TOFWork, which is a online process monitoring system, and does a little bit of work on sort of gas and volatile monitoring. But primarily their interest is in DART, and they've also demonstrated DART on everything from the EvoQ up through to Tim's TOFs and things, and they're doing some interesting applications with their ion mobility systems as well. On to thermal. They have the Very spray source, which started life once upon a time as Prosolia Velox source. When Prosolia IP was bought by Waters, the Velox stuff ended up with Thermo, and that was developed as the Very spray. I had to double check because the Very spray there's not many publications. There's only 50 or 60 publications out there using the Very spray. So I contacted a friend at Thermo to ask, is it still on the market? And he's like, yes, it's still available for sale. And they're hoping to include support for Orbitrap family, specifically the Explorers family, at some point in the sort of mid-term. So it's not imminent, but it's a goal of theirs. But it is supported on their TSQ family. And paper spray is really good because it's really well suited to things like blood spot analysis. You can just get your blood spot, put it onto, typically it's something like a chromatography paper, then you pass an electric current through it. Similar sort of electric current that you would find in the capillary or nozzle of an ESI source, and that then puts your charge onto the analytes of interest, and then they're introduced into the system under vacuum. The nice thing about the Very spray source is it's got this really nice stack loader system and can get through decent numbers of samples very, very quickly. What you'll also find if you venture into the depths of things like analytical chemistry or the Journal of the American Society of Mass Spectrometry is there's a lot of homemade sources on thermo instruments as well. And the source design just really benefits from that. You know, the source is pretty accessible physically. You know, it's easy to get to the source. It's not covered by bits of plastic, and you don't have all the desolvation stuff getting in the way. It's relatively easy to get, and you can put stuff in front of it. The ion optics immediately behind tend to be pretty robust. They don't tend to get too dirty too quickly. And you've got all of the usual Orbitrap benefits of high resolution, so you know, not having chromatography is less of an issue, and you've got pretty fast scan speeds and things. And also, I suppose, tends to be quite a few people that tend to have an older Orbitrap working around after they've upgraded. So there might be an old instrument at the back of the lab that, if it does get broken by doing some sort of crazy experimentation, it's less of an issue. They're not losing their main workhorse. So there tends to be some interesting stuff, and as I say, I would encourage you. I mean, there's in total, I think at the last count, there's probably like 300 or 400 different ambient techniques in terms of acronyms and things. There's a variety of different papers that cover what they all do, and they can be split into different ways. You know, and there's sort of all sorts of acoustic injection and huge variety. So we're only just scratching the surface, but these are the ones that you're more likely to find, because they've got vendor support. You're more likely to find them on posters at something like this or ASMS. Agilent, a bit late to the party, I think, when it comes to ambient. They've got an atmospheric pressure MALDI source, which just meets the definition of an ambient ionization technique. Because the sample's kept at atmospheric pressure during the sample introduction process. A company called Mastech offer that in partnership with Agilent. It's more just a convenient way to do MALDI on a Agilent instrument without having to buy another MALDI, rather than offering anything hugely impressive. But the cool stuff is the secret, which there's a partnership agreement with Plasmion and Agilent to sell for food and environmental applications. And Plasmion actually have their own software that they can flash onto an Agilent triple quad or single quad, the IQ or the Altivo. And they can do their own chemometric modeling and rapid analysis stuff. And they put it into a dedicated and pretty funky looking black box, and they call that the Havoc system. Others, so I apologize to Japanese friends who are more familiar with GEOL than I am. GEOL don't offer mass spectrometers in the UK, European market, so my exposure to them is a little bit limited. Chip Cody and the guys that developed the DART system originally worked with GEOL, and GEOL did have, I think it's still listed for sale, the Accutov DART. So it's again, it's a little bit more integrated, but it's not as fully integrated as the Bruker DART system. Again, Shimadzu, not quite as familiar with Shimadzu's offerings, but there's nothing that I can see in their catalogue that would match the stuff like Waters and Bruker and that. But companies like Secret, companies like Plasmion offer the Secret source, and there was a DART source for the Shimadzu. Not aware of anything at all from PerkinElmer, but as I say, custom and homemade sources may exist for those. SciEx don't have any in-house aims, but they do a really nice DIMS system, which is the acoustic ejection, the echo, which I'd be shocked if there's not a SciEx poster somewhere here talking about echo and how they've managed to screen 70 billion samples in 5 minutes or something with the echo, because they're getting really, really quick with it. And that fits on to things like the 6500 triple quad or the Xenotov 7600. And that's probably been updated in the last 2 weeks as well after ASMS, and I'm slightly behind with that. But I did check all the websites, but ASMS updates are not just quite feeding through to everything yet. Because I know there's a new or an updated 7500 plus triple quad out from SciEx as well, which probably is echo compatible, but don't quote me on that. So very briefly, the types of analysis, what can AIMS and DIMS actually do now? You can do sort of targeted analysis, and this is where we do what we call MRM screening. So unlike in normal LCMS-based mass spec, where you work out your retention time for your analyte of interest and you set your retention time window for your MRM, what you can do with ambient and direct injection is you set the MRM window from the start to the end of the run, and you look for those parent and fragmentation pattern daughter ions throughout the whole run, and you'll find that you get, in the case of the Sudan dye plot there, that's done with a DART source, actually is with the mycotoxins as well, and you get a sample, and it goes to the next sample, and it goes to the next sample, and it goes to the next sample, and you can see that we've actually analysed with the Sudan dyes and with the mycotoxins, we're analysing a sample roughly every 20 seconds. And all we do is we look for, in the case of Sudan dyes, 4 Sudan dyes with 3 transitions, so there's a total of 12 MRMs to look for. With mycotoxins, it's a little bit more. I think there's something like 16 or 18 MRMs in there. You have to be careful not to have too many MRMs running, because you're not now doing a small number of MRMs and then going to another set of MRMs and then going to another set of MRMs. You have to be careful not to have too many running, or you'll lose sensitivity. But the speed of analysis means that you can just have one block of MRMs and then just repeat for another block of MRMs instead of trying to separate out things. So even if we have to analyse the sample 3 times at 20 seconds per sample, we're still analysing the sample for 1 minute, so it still makes it a very, very quick analysis. If you've got sort of familiarity with things like dynamic MRMs, where it'll update retention time and things to cope with small changes in your chromatography, that sort of stuff doesn't work with AIMS and DIMS. And my colleagues Vera and Nicolas will talk about the challenges that are going to come from not having retention time. But safe to say quite a lot of vendor-specific software really doesn't like not having different ions coming out at different retention times. It gets very upset, very confused when you start having the same ions coming out 5 seconds and 10 seconds and 20 seconds and 40 seconds, and the software can sometimes get very, very confused, which creates the challenges. And that's really behind this workshop. So you can go targeted and you can look for specific compounds. Obviously, you can do untargeted analysis and then start building chemometric models and just process the data. So you can do full scan stuff, and you can do all of your conventional, you can do DIA stuff, you can do anything that you can do with a LCMS, as long as you're not reliant on time sectoring. You can do with an ambient ionization source, and you can also do with direct injection. And for applications there, we can do things like safety, so we can look at mycotoxin contamination just on a full scan basis. We can do quality by looking at different whiskies and looking at adulteration, if people have been putting in methanol to dilute stuff down. And we can do geographic origin, adulteration, to detect fraud for commodities. And on the right-hand side, that's actually pepper that we've done. And these are done with, we've got the volatile analysis, so we've got plasmion source for the two on the left, safety and quality, and then that's DART over on the right-hand side for fraud. Where it fits into a sort of workflow, I would suggest, and this is a good starting point, obviously once you have your own applications and your own development, you know, I would encourage you to sort of go your own way on this. But do a rapid screening first and get hundreds or thousands of samples through. Find out the ones that you think might have a problem, ones that are suspicious, ones that are of concern, or ones that are completely free of contaminant, free of an adulterant, show no sign of having a marker of interest, and then put them back in the freezer and forget about them, and leave samples for more thorough analysis that you think have some sort of quality that you're interested in, whether it's they've got a fraudulent application or whether they've got some sort of biomarker that you're interested in. So my suggestion is you do a rapid screening first and then gather up a small number of samples that you're most interested in, that are most promising, and then do your LCMS, your GCMS work, find out what's going on. And you know, that's when you're maybe going to do an untargeted run with the LCMS first, get nice separation, or maybe even go straight to running it through a triple quadrupole and quantifying the issues if you've identified analytes of concern, whether it's an aflatoxin, for instance. So, right, okay, let's measure how much is there accurately with an LCMS technique. Perhaps you've got an ISO accredited technique that you need to use. You know, then throw it in that direction. Then it's possible, and Nicolas in particular will tell you about this, you know, the data fusion and how we can make use of the data that we gain from the rapid analysis to drive how we work with the more conventional analysis as well. So, getting towards the end of my presentation, you'll be pleased to hear. So, how to get the most from AIMS and DIMS. So what works and what doesn't? So one of the big issues is there's a little bit of a lack of understanding about what will ionize with each new ambient source as it comes onto the market. Most new sources tend to be energistically very low. So we've got things like cold plasma. The secret source uses a nitrogen air plasma, so it doesn't have the same energistic punch as the DART plasma, which can use helium. Some of the sources can struggle to promote ionization. So you'll tend to find that sources struggle to ionize larger molecules, particularly molecules that might need more than one charge to get something to fly. Unusual, but not unheard of, to see ambient sources causing fragmentation, and you can promote fragmentation by going in the standard direction, you know, doing the source in-source fragmentation, ramping up your source voltages and things. So that's out there, but you know, whilst we know, and there's, you know, obviously the Metlin libraries and things, we know what works with ESI and EI very, very well, and there's hundreds of thousands of papers with individual analytes and sort of source conditions to get them to ionize. Less well understood with some of the ambient sources, so there's a little bit of a void, and if you do embark on doing ambient ionization work, you'll find you do a little bit of work to find out what settings you need to use to get analytes of interest to ionize. Things like software integration, so using Mass Hunter here as an example, if I wanted to do Dart, it looks no different. There's no option in Mass Hunter to control a Dart source. There's no option in Mass Hunter to control the secret source. It's the same for mass links with waters. It's the same with thermal. It's the same with all the other guys. The only people that have integration currently for an ambient source is Brooker with the Evoke Dart. This means that you tend to end up having a notebook and you start to scribble down settings for your Dart temperature or your secret voltages and things, because they're not stored in a method file alongside the actual mass spectrometer methods. They're not stored in the data file, so if you forget 6 months later, it's like, did I have that set to 250 degrees or is it 300 degrees? If you haven't written it down and saved it somewhere, it's not saved in a data file anywhere, you won't know. So it can be very, very difficult to record the parameters and to control the instrument in the software. So one thing that we're constantly begging for from all vendors is better software support, better integration. Obviously, direct injection doesn't suffer from anything like the same problems on the acquisition side because you're using the same source option and things, but it does suffer from the same data analysis options, which you're going to hear about in just a second. So coming in sort of in the future is what to look out for. So there's going to be more laser ablation. You know, as lasers become cheaper, smaller, more effective, you're going to find that there's more inclusion of lasers as a way to volatilize and ionize samples. And then I think there's going to be a little bit of talking about direct injection. You're going to go somewhere a little bit with a little bit more chromatography, so you get a little bit of separation, but still a very, very rapid system. So there's adjunct of a quick probe GC system, which has an incredibly short GC column and can do very, very rapid analysis, but still gives a little bit of separation, a little bit of work maybe on using things like LC guard columns just to do a tiny little bit of separation, or some sort of 3 centimeter columns as well, to get high throughput, but also maybe just get a tiny little bit of separation, maybe to remove some of the issues of having matrix in your samples. So to conclude, for my part of the talk today, I think ambient and direct injection isn't going anywhere. And I think integration and the sales operations from vendors are going to get better, and I think uptake amongst end users is going to increase significantly. I think that's partly driven by the cost of instrumentation. The idea of getting enough budget now to buy 2 or 3 instruments for different tasks is becoming harder as instruments become more expensive. So being able to do more things with one instrument by swapping the source and maybe get higher throughput, so you're not reliant on having 2 or 3 instruments to get throughput, is going to drive that. The techniques are complementary. They don't threaten LC or GCMS. They can add to the repertoire of what you can do in the lab. And as I say, if you screen and then find the samples that you're most concerned about and most interested in and focus on those with your LC or GCMS, I think that's where AIMS and DIMS complement LC or GC very, very well. It is important to choose the applications for AIMS and DIMS wisely to get the best from any investment and think about what sort of source you're going to buy and stuff, especially if you're going to purchase new hardware. Think about what's best. But the good thing is, the technology tends to be relatively inexpensive in mass spec terms, and it's a really useful way to get through high numbers of samples, introduce new types of samples to your lab, or perhaps attract new collaborators by being able to analyze samples that previously would have been a little bit too difficult or time-consuming to put through your existing instrumentation. So that's all from me, and Lynn's going to come back and introduce our next speaker.
So thank you, Nick, for this very nice introduction. Now everybody's aware on how both AIMS and DIMS systems work. We're going to dive a bit more in depth into the data analysis now with Nicolas Defooz, who has been working on REAMS, more specifically data analysis, for almost 4 years now. Has developed quite some, let's say, strategies to get that running, and has also done some benchmarking with existing technologies. I'm going to open your presentation. Yes. Yeah, it's like a special format with R embedded, not something I'm used to work with. Is it okay like that? Or you need it a bit more left? Or? Yeah. Yeah, it doesn't want to. Yeah. Voilà. Okay. Here you go. So.
Okay, good morning, Osaka. Thank you, Dr. Birse, for this wonderful introduction on all of the AIMS and DIMS instrumentation options. A small disclaimer before we start. I'm a bioscience engineer by education, so it means that you'll maybe see a bit of the engineering outlook reflected on some of the contents of this talk. Before we start, I would like to introduce to you Aidan. Aidan has indulged in quite some fast food over the last few months and years, and now he's wondering whether he might be at risk for developing severe health risks, obesitas, diabetes type 2. So to know whether he is at risk, we might use ambient ionization techniques to look for biomarkers. And before we can embark on that exciting journey, which we'll talk more about in the next presentation, we also first need to understand the raw spectral data and really understand what is in the data and treat the data with respect as well, and really uncover the truth in this type of data. So what I want to do in this talk is to start unwrapping a bit of the opaque veil that still lies over ambient ionization and give some recommendations on both a qualitative and a quantitative handling of these types of data. So before we start, I would like to do a small pop quiz. If you have this particular mass spectrum, is there anyone in the audience who can tell me with absolute certainty the identity of this compound? If someone is vehemently nodding no, know that they have a bit more of a negative outlook on life, but they have some truth. Without the chromatographic separation, which is inherent to AIMS and DIMS applicabilities, it's very difficult to annotate features. But what I hope to accomplish in this talk is show you that we shouldn't be content with not knowing at all what a compound is, and that there's more truth to be uncovered in the raw spectral data, and that we can at least narrow it down very much from a very complex sample with maybe a few thousand features, and that we can at least generate some hypotheses to then drive more traditional LCMS, GCMS workflows to further dive into what might be at cause for example, a particular health profile. Forgot to go through the options, but still see that the slide is a bit. Oh.
Ja, Maxi.
Ja. Dat is een beetje te groot. Gewoon even onder, omdat ik denk dat het anders een beetje. Ja, dat is juist goed. Okay. Thank you. Okay, so we had some options, but still very difficult to see. If we look a bit at how this data looks like, if you see these two mass spectra acquired on a different day, it's quite easy to correspond to the different features. The peak shapes are still quite okay, so we could easily say that, I mean, the mass peaks correspond between days and we can link them and correspond them together. But if we look at a different mass spectrum, it already starts becoming much more difficult. Where does the peak end? Where does it start? The peak shapes start becoming ill-defined, so it really becomes more difficult to see, is it a true mass peak, is it a noise feature? And as to start annotating it, it really starts to become difficult. And this is even only between two subsequent days. If you analyze over a longer period of time, it might even be more difficult. Same here as well. Peak shape is ill-defined, often for at least low-quality intensity peaks, but it's not because they're low-intensity peaks that they're not interesting from a chemometric perspective. So to focus a bit on the content, we'll discuss a bit of the different software solutions, both open source and some vendor options as well, and then some general recommendations from my part on how we should best handle these types of data, but of course, maybe there's better strategies so we can discuss in detail. So we'll first look a bit exploratory at the MS data, see how it differs from a chromatographic perspective in the LCMS scheme, and then some typical challenges related to the non-chromatographic types of data. Discuss some peak picking solutions, both vendor-based. I'll focus then on progenesis for the data acquired with Waters instruments, such as, for example, the REAMS, and then some options in XCMS, so in R, to process there, as we have some bit more control over the different options in the peak picking steps. And then we'll discuss the feature annotation only on an MS1 level, to show that indeed we can have some results, discuss a bit of the quality assessment of features. Is it a true biological peak? Is it not? How can we know? And then we'll discuss a bit of the alternative approaches to the data preprocessing that we've been developing in Ghent and how they might add an extra perspective to what is already available and how we can uncover more from the raw data. So first, some exploratory MS data analysis. So you use an ambient source to analyze a sample, and you'll get what you would say is a chromatographic peak, but it's not really a chromatographic peak. It's more an ambient peak, where we'll acquire a couple of mass spectra over a very short amount of time, typically for sure less than a minute, and even close to 15 seconds, with then an ambient peak profile. All of the ions are measured simultaneously. They are all introduced to the mass spec at the same time. Of course, before the ambient, before the sample measurement, we acquire more the chemical noise, the instrumental noise, which is of course of no biological significance. But then at the top of the ambient peak, we have a biologically informed mass spectrum, which we can then do our data preprocessing on. But as you can see, there's quite some variability across scans, which can also happen, depending, of course, on the source, on the ionization. If you don't account for it, it can also have a negative influence on the reproducibility, which we'll discuss a bit more in depth as well, on how we can counter it, and at least from a data analysis perspective, take into account this reproducibility and be as fair as possible. Of course, it's also an instrumentation option that reproducibility also has to be in check. So how can we improve then the reproducibility of the scans? So both the acquisition parameters from an instrumentation option, the ionization. So for example, in the REAMS perspective, it's then often the laser energy. How well energized will you ionize your sample? Or simply increasing the scan time, as you will kind of average out the individual differences and you acquire the signal for a longer time. So then, of course, you can wonder, where should we start our data pre-processing adventure? Should we only focus on a single scan? And then the most obvious choice would, of course, be to focus on the scan with the highest summed intensity. But it's also very limiting because you don't focus on the whole data set that is available. So we might focus on the whole chromatographic ambient peak, or maybe only part of the peak because we don't trust the entire part of the ambient peak. So there's different options there, both with each of their benefits and their disadvantages. So some challenges, as we discussed, which region of interest should we focus on in the chromatographic sphere? It's more easy. You will at least have multiple chromatographic peaks. Of course, multiple compounds can elute at the same time, but here, single scan, multiple scans. As we will discuss in much more detail, the lack of chromatographic separation and the simultaneous introduction of all of the isotopic species, all of the adducts, and just all of the ions really makes feature identification very impractical, and there's a lot of effort needed to correct for it. And as we slightly discussed already, we really need to take into account these mass deviation shifts. Of course, depending on the TOF analyzer or whatever mass analyzer you're using, it might be more severe or not, but at least maybe it's a bit of the environment in Ghent, I don't know. But the intra and inter mass batch deviation mass shifts can at times be quite severe, and we need to account for it. If your data is more perfect, so the better, then all of the solutions will also work. If it's not, then at least you should account for it. What is a more traditional way to deal with it would be through a log mass correction. There we would add a specific compound with a known exact mass, and then we can correct a shift all of the mass peaks according to the relative deviation between its known mass and then the measured mass. However, we do not endorse the use of an external log mass, as it can sometimes influence the ionization efficiencies of the biological features. So we'll discuss a bit more in depth another possibility, making use of no externally added log mass. So as you can see from the figure as well, was all analyzed on the same day, even within a few hours, and you see really severe mass shifts, which makes feature correspondence really difficult between batches. Mass peak that you detect in 2 different batches, and even between 2 different samples. Can we be sure that it corresponds to the same feature? Without lack of chromatographic separation, which you can also have the retention time as information. It's really difficult. And as we will see in a bit more detail, AIMS and DIMS technology really has the applicability for real-time monitoring. And then this, is kind of a bottleneck to me personally. I don't really like it, and I get a bit annoyed by it. So how should we then deal with it? As we discussed, maybe the scan with the highest ion count would be the most informative. And then the easiest solution, and also a solution that we implemented in our own laboratory, as it's a very easy solution, would just be to bin the data. However, again, variability across scans will lose this variability, and we distort very severely the accurate mass, rendering annotation effectively impossible, at least on an automated perspective. And without a log mass compound, if we have large inter-batch mass differences, we'll have to use large binning windows, which will also reduce all of the spectral information that we have. But of course, it's very easy. If you look at the left side, the raw spectral data, and then you apply some binning on the right side, and we lose a lot of the intricacies on how the spectral data looks like, the accurate mass is lost. But I must say that from a chemometric profiling perspective, we can often have at least very decent models. So it's not, there's still very much use to it, but there's some limitations to it as well. And it's, you must choose whether you find one thing more important than the other. But it's a very simple thing to do. But of course, there's no distinction between biological peaks, noise mass peaks. You effectively bin all of the data, you include all of the data. the accurate mass is lost, the feature information is also lost. But of course, we can do some basic feature filtering. We can apply an intensity threshold or filter on a coefficient of variation, but it will still include some noise peaks. We might also filter out important biological features. So it's a bit of an arbitrary method, but still works, but not as perfect as you would like from an informed way of handling, at least from my personal perspective. So what are then some more advanced peak picking solutions? Let's start with the vendor-based peak picking solutions. I'll just focus on Waters and Agilent here to highlight two. So Waters, the reams that we'll be discussing a bit more in detail, which then uses Progenesis and Mass Hunter for Agilent. Just to show very briefly for Progenesis, if you would, for example, analyze or do two sample measurements in a specific sample, then we can first split the file into two separate sample measurements, two separate burns, for example, technical replicates. And then in the software, we can either do a external log mass recalibration, do some adaptive background subtraction, all very intuitive to use. But of course, we don't know as well, but Progenesis is also used in an LCMS application, so it's likely developed for an LCMS. They do have options for direct sample analysis, but it's a bit of a black box approach. I mean, we don't know what is the algorithms behind it, and as well, at least from an aims and DIMS perspective, the accurate masses, when you analyze large batches and large cohorts, are distorted after processing, which renders, again, the feature annotation more difficult. And there's little to no user control on the peak picking, which makes it user-friendly as well, but also from an informed perspective, makes it more difficult. But of course, there are advantages to it. The software is fully integrated, so it renders a streamlined workflow. It's easily obtainable as well, and I mean, the vendors will support their software. And same with the binning as well. You can have valid chemometric models with the software solutions. It will not make or break a model. If it would, I would rather say that the data is quite bad. But there are small intricacies which might have bad reproducibility if you use one or the other data analysis pipeline. But on a global perspective, it's not all too bad. So there's no custom approaches. There's more of a one-size-fits-all solution. So there's benefits to it. If you want to use other options, open source, Metabolomics software, MS-Dial, or others, you can. But you might have to tweak the data a bit to fit the AIMS data to an LCMS sphere. But I think the adagio of my talk is also becoming clear a bit that I'm not a fan of the existing solutions. So both because the methodology is based on a chromatographic dogma, which is not true from an AIMS perspective, as it's an ambient peak and all is measured at the same time. The algorithms are unknown, which renders a comparison between labs, which might have done different instruments with the same samples available to them, difficult. Each software has its own tailored solution, so own results from a software perspective. And at least from a feature correspondence perspective, non-flexible. If you want to do these real-time analysis, you analyze one batch, you analyze the second batch, and each feature will be characterized by a slightly different MZ value, and it's up to an expert to say, they're quite close together, probably they will be the same, but it's a bit arbitrary. So this integration of multiple batches, it's impractical, certainly on automated level, it's difficult. So this traceability issue between the raw data and then the processed data, it's difficult and it requires a lot of effort to really trace it back. I mean, you really have to look at your raw spectral data. I've spent many hours just looking through the text files with the numbers to trace back what is really happening. So it can be quite challenging at times. So, of course, the ambient peak does correspond or looks like a chromatographic peak, so we might, and at least the vendor-specific software does it as well, can we not treat it as a chromatographic peak? So I'll dive a bit more in depth with XCMS, as we have a bit more control over the different processing steps, and we can inspect all of the data at the different stages of data analysis, which is of course also very good for Aidan, because if you find a biomarker, then he'll be happy. So you can see here an extracted ion chromatogram for 4 randomly selected features, not randomly but informed. And you can see that in about half of the cases, the peak shape is ill-defined, like it's kind of cut off, and it's not the nice Gaussian profile that we expect from a chromatographic peak, which is in part also because it's a very sudden increase in ions that happens. It's not a more gradual increase in ion intensity as in a chromatographic separation. And of course, the number of scans is also very limited. It's a very short sample measurement time. So if you then do the effective peak picking itself, just some code to demonstrate, but it's not that important. If you do it in XCMS, you get a table which then characterizes the mass peaks in its retention time. Retention time, of course, being then the scan time, but it's not really relevant in an ambient sphere, intensities, and then in which samples it's detected. Of course, for the abundantly available glucose sugar, it's very well detected in all of the samples, which was also to be expected because it was one of the most intense mass peaks in the sample. If it wouldn't have been, would have been a real issue. So all good there, no issue. But if we then, and also nicely corresponds to the thick profile of the ambient peak, so no issues there. But if we then start looking at another mass peak, more a lipid, then we can see it's only detected in 2 out of the 4 samples, while it does have a nice mass peak shape in the individual scans. So the feature is for sure there if you manually inspect it. But in the chromatographic detection, it's not detected as such. But of course, yeah, a bit the shame as it already fails there. And then where will it fail in different aspects? So if we then do the peak picking on the whole data set, we get about 2,500 mass peaks, which is about what we would expect per sample. So not out of 4 samples, but per sample, at least for the data that I'm showing here. And you can also see that the distribution of peaks detected per sample is quite skewed. Most are only detected in sample 2 and sample 3, and on the sample 1 and 4. So already shows that there's something lacking. They were not detecting the peaks, while even there should be there. So probably through tuning of some parameters in XCMS, you can achieve a slightly better result, but I've not been able to do so to a very larger extent. But if there's anyone who can correct me, I would gladly know. So if we then group all of the mass peaks into features, we only get about 600 features, which is way too low for what we would expect. And again, you can see what we had expected as well, is that each feature typically only has 2 to 4, but we would have expected for all of them to be closer to detected in all 4 samples. And that there's also some features which have then like 5 or 6 mass peaks attributed to them, which is also not possible that we group more mass peaks to a feature than we have samples. So let's look a bit more in detail what's happening there. So just to show for one particular feature which mass peaks have been grouped to that feature. And if you look very closely, you can see the chromatographic peak that it's detected in gray, and then the scaled stick profile in red. And you can see that it doesn't nicely overlap with ambient peak, so the sample measurement peak that we had. And if you look more into detail in data, it's effectively a noise peak, which was measured in the scans prior to the sample measurement, that has been grouped together with the ambient peak, which is of course not wanted as well, that we're including noise features from before the sample measurement in our own, in the actual ambient peak features. So already there, not the kind of result that we want. So kind of disappointing. And then if we look here, you can see 2 very distinct mass peaks in the mass spectrum, but still they are all both grouped then together to the same feature. So again, here not wanted. The true biological mass peak would have been the blue one, and the green one just a noise feature. but it again shows the difficulty. We have a lot of mass peaks bunched very closely together in the mass spectra, which renders it very difficult for peak picking algorithms as well. So if a chromatographic method isn't well suited, maybe we can then just treat it as a single spectrum, the spectrum with the highest summed intensity as we discussed before, and then do the peak picking in the MZ dimension. And also there, XCMS has some options for it. And we already get a lot more mass peaks, about 11,000. But only for about less than half of them, we can calculate some quality metrics, which is also an indication that only for half of them, the quality is quite okay, and the other ones will very likely be noise features. And without showing the results for sake of time, we do detect these mass peaks more uniformly in all samples, which is an improvement over the chromatographic detection. So when we look a bit more in detail and we then group them into features, we get about 3,000 features that we find over the spectra. But when we again filter for the ones for which we could calculate some quality metrics, only about 2,200 remain, which is also quite less than what we would expect, closer to 2,000 or even a bit more for these types of data sets. But they are at least more uniformly detected in the samples. So it's a valid approach, but of course, also again, only focusing on a single scan, so you might lose some of the variability across scans for then a feature quantification perspective. So an issue that is quite close to my heart is the feature annotation, because when I started with AIMS, I was like, okay, we can analyze samples rapidly, and then we can have biomarkers, and we can annotate them, and all is going to be fine and well. But of course, reality showed to be a bit different. I think we can all agree that for the 4 different mass peaks that we see, they all correspond to the same compound. They overlap quite well in the MZ sphere. But the peak apex is all represented by quite a different MZ apex. So then what would the accurate mass of this compound be? So a good estimate might maybe be like an average of the different MZ values. But when you then start to query databases, you have to use very large ppm windows to find an actual compound. And if you have a couple of thousand compounds in your data set without the chromatographic separation, with adducts, isotopes, all starts to become very, very difficult, and you will get thousands and thousands and even millions of false hits in databases, which is just not feasible. So what might be a better solution? Maybe we can fit a composite spectrum, so like a summation of all the individual spectra, and then use the MZ value of this composite spectrum as a better estimate. But even there, you still get quite a lot of false hits. And a better estimate would be to fit more of a Gaussian distribution to it, as we, of course, also would expect all of these mass peaks to have a Gaussian distribution, and certainly for the larger intensity mass peaks, they do, but for the lower intensities, they don't, because you have this variability across mass peaks. Of course, depending again on mass analyzer, might be better for one, might be worse for another, but let's again assume the worst in our data. And without going too much into depth, we've obtained quite well results in the feature annotation through adopting this approach, and even within small ppm windows of about 5 ppm, we can narrow it down to only a few options for a lot of the features that are present. But I'll dive a bit more in depth just a bit later. So we're still dealing a bit with the issue, and we'll never solve as well. Is a feature a true feature? Is it a noise feature? It's always going to be difficult, and I think nobody has a right answer, but I think, at least from a theoretical perspective, each mass peak, maybe not on an individual level, because certainly for lower quality signals will not always be the case, even though they are biological, but their composite spectrum should at least resemble a Gaussian curve, and then we can use some signal-to-noise ratio cutoffs, and maybe also do some background subtraction with the mass peaks that we analyzed before the sample measurement, and then if they're still above the threshold, then we can retain them or not. But we don't have that many quality metrics to judge a peak on its behavior or its identity. So then, of course, it's also from a chemometric perspective, interesting biomarkers, interesting features that occur after the modeling will, of course, be the first focus to focus more on in depth. So with the time remaining, I would just like to go a bit more in depth over the alternative approaches that we've been developing in Ghent, and where we think that they might add a bit of an extra edge to the raw spectral data preprocessing. And to introduce it, I'll first dive a bit more in depth on this. It's an approach that we've adapted from literature, which effectively renders the use of an external log mass not necessary, as we will use the inherent information that is available in all of our mass spectra as log masses, so kind of digital log masses or hook points. So what you will, of course, again, depending on the mass analyzer, but typically there are minor discrepancies between the spectra, as we saw with mass peaks, each slightly different MZ value, which render this comparative analysis difficult. Again, easiest solution, binning, not a fan. So can we identify hook points which are then recurrently, consistently, always present in the mass spectra, and then we can use those to correct these variations within the spectra on then a spectrum-specific correction. So these hook points always present, and then all of the peaks in between, then we can do linear corrections in between these hook points to correct these slight minor discrepancies between the spectra to aid us in this comparative analysis, and then maybe do like machine learning or something else. So how does it kind of work then from a data analysis perspective? Again, all of the batches have slightly different MZ values. So choose a reference data set, typically a pooled QC data set, and define a spectral representation point of which you say, okay, this feature will characterize it by this MZ, which would then be designated by this yellow line here. And then within a small ppm window, start grouping peaks which are then within this spectral representation window, but only within this window and not outside, not to group mass peaks which do not belong there. So the mass window has to be quite small, not to overlap with other mass peaks. So of course then we can do this in one batch and detect different mass peaks. And then if we have a different batch analyzed next week, okay, then you might say the mass peaks colored in green correspond to the same features in this slide. These and these, they are the same compound. Of course, I've kind of set you up for failure. If you would look at the entire data set, you'll see that there's an inherent inter-batch mass deviation, and it's all shifted a bit more 100 ppm to the right. So again, be careful for it. So first, we have to correct for these inter-batch mass differences, because otherwise you're just combining mass peaks into features where you don't belong to. Your chemometric profiling will also incorporate these mistakes, might deal with it because it's very complex data with a lot of thousands of features, but it's just not correct from an informed perspective. So first, correct for the inter-batch mass differences. So I'll quickly go through some code, and I hope to make some of the data preprocessing approaches that we're developing public quite soon. So we need both the raw spectral data preprocessing and then the centroided data in all of the different steps that we have. So on then, for example, a pooled QC set, because it's the most reproducible as well, and then on the scan with the highest summed intensity, identify these hook points that we want to use for both the inter-batch mass correction and then our spectrum-specific mass corrections. And typically we get quite a few of these hook points, a couple of hundreds of them, which is then nicely uniform throughout the mass scale as well. So determine these allowable mass windows within which we can then group these features for feature correspondence and the spectral representation points as we did before. And at least it kind of ensures, and we'll go kind of ensures that only mass peaks which belong there are grouped together and not mass peaks which are too far apart through all of the mass correction, both inter-batch and spectrum-specific. So first correction for the inter-batch, both on a loose or a linear perspective, and also using these hook points to correct for this without an external log mass. And then we might have that some mass peaks still fall out after the inter-batch mass correction outside of these allowable mass windows that we have set up. So that's why we needed the spectrum-specific mass correction to first group them a bit better together, and then they fall within this allowable mass window, and then we can group them together as the same feature, and we can be quite sure that it's indeed true. So we can also use this composite spectrum also to estimate the peak boundaries of the peak in the MZ scale. And this both helps for the accurate mass, but also for the feature quantification, as I'll discuss a bit more in the next slide. So we can nicely say, okay, this feature goes between, what is it, 428.0 to 428.0607. So feature quantification, we've started this talk with, should we focus on a single scan? Should we focus across part of the ambient peak? And I can say that for better reproducibility of your data, it's better to focus across the ambient peak and some of the different intensities across the scans. In a typical LCMS metabolomics scheme, you would of course create an EIC on the centroided intensity, but we've seen that it's better to integrate the peak area in the mass scale in each individual scan, so a bit of a different approach than the typical LCMS metabolomics, and then sum these individual peak areas across the ambient peak and use that then as a feature intensity in your feature table. So compound annotation, of course, reality is also difficult. So if you really want to go and query databases, you will likely need a matrix-specific compound, for example, a glucose, and then just shift towards this glucose. But together with everything, the inter-batch mass corrections, the spectrum-specific mass corrections, and then a matrix-specific mass correction, we do get quite some good feature annotation results. And won't show it here, but we've also been able to quantify in the yeast data sets about 1,000 features with the isotopic features as well, with adducts as well, and we can really narrow it down to only, let's say, a handful of different options per annotation or per compound, a lot of which are chemical isomers. So is this a molecule? Can we identify it? I could also go again through the different options, A, B, C, D, and E. Will we ever be completely sure? No, on an MS1 we won't, because of course chemical isomers, I think there's two distinct chemical isomers here, but the other ones are just different conformations. We'll never be sure, but at least we can narrow it down to a handful of molecular formulas and then go more in depth in a traditional metabolomics sphere. And it just helps us quite a bit forward, whereas without conventional approaches, we're really at a loss what a feature might be, and at least this helps in identifying might be a biological one and also guides the biological significance of the feature as well, which I think is very important and also very near to my heart. So some take-home messages. Whatever software you use, each has its benefits and disadvantages. Consider the ease of use, sensitivity, selectivity criteria. Be aware of how your data looks like, the differences, and account for it. Don't just blindly do the data analysis, do the processing without not thinking about it. If you want to go to feature annotation, a lot of work, but it can be done, and hopefully I can share some tools with you quite soon. And also we look at how we treat our data from a feature abundance perspective towards the reproducibility. And just to very simply say it, look at your raw data, play with it, understand it. It takes time, but treat it with respect, because if you don't and you just blindly do your subsequent data analysis, I mean, it's just not right. So to end on that, I would like to thank you. If you would like to know more both on the data reproducibility, the feature annotation results that we've achieved, which I haven't shown here for sake of time, talk to us in the Q&A. Come and join me at Post 2002, and then we can discuss a bit more in detail and show some of the actual results that we've obtained in this workflow. And with that, I would like to thank you for your attention. Thank you.
Thank you, Nicolas, for this very elaborate explanation on your novel methodologies. Then we'll end our workshop today with a presentation of Dr. Plekhova. She will give a bit more insight on some of the, let's say, reproducibility issues at the instrumental level, of how that unfolds when you develop your own systems, and then some applications. But we might want to limit the applications a bit for the sake of time, to leave some time for the Q&A. Okay, thank you.
Okay, thank you for the introduction. All right. Perfect, thank you. Good morning, everyone. It's great to see you here. My intention today is dive a bit deeper into practical aspects of data generation and data handling on based on a couple of cases. And the star of our show is laser-assisted rapid evaporative ionization mass spectrometry, and we heard about it in a couple of presentations before me. So what does it look like? Well, we have our ionization source connected to the mass spectrometer, we have our solvent delivery system, and we have our laser ablation station. At the level of laser ablation, we have our sample under the laser focus point. The transportation of the laser energy on the sample surface will rapidly heat the sample, creating a vapor. The vapor will be catched by the sample transfer tube and transported to the level of the source. Here, the sample vapor will be mixed with the solvent matrix. The solvent matrix serves two main purposes. First is to dilute the sample vapor, and second, to promote ionization of single molecular species. This sample solvent mixture would then transported through the ion optics further into the source and heat a heated coil for creation of individual charged species and additional ionization and declustering. Then the ion optics will transport the charged species to the time-of-flight mass spectrometer. Now, as we can see, we have three major parts in our installation. It's the solvent system, it's the laser ablation station, and the MS. In the applications involving fingerprinting, so untargeted detection of everything we can detect within our sample, what do you think will be major attention points? I can give you a bit of a spoiler. It will be laser ablation system and it will be a solvent system. Now, I want to start with the laser ablation, but it's such a huge topic, I don't know where to start. But the rule of thumb here is that the more energy you apply to your sample, the higher intensities you will get. You need to be aware that although the desorption event is very energetic, you might end up with higher laser energy at a very high rates of fragmentation. That's one of the limitation points. The other limitation point is that your huge desorption event might oversaturate your ionization source, which will lead to the loss of data quality in terms of repeatability and reproducibility. But there are a lot of smaller things to consider, like in this example, it's the atmospheric pressure multi, and the samples were spotted either on a glass receptacle or on a metal plates. With the peptide standards, no signals could be detected on a glass substrate, but could be detected on a metal plate. So even the receptacle of the sample can play a huge role in your data and your data generation and as subsequent data analysis. The other thing to look for is the wavelength of your laser, and this is something you need to consider together with your sample matrix. So what type of wavelength your sample matrix will absorb best. Now, moving on to the solvent systems, a lot of studies before us showed that both the flow rates of the solvent and the solvent composition will have a huge impact on detected intensities. We also tested it for our sample types in the initial proof of concept experiments, and we saw indeed that with different solvent composition, we get from the same samples different number of detected MS peaks. Now, I told you that MS parameters are least important, or at least that's what we saw in our biofluid optimization experiments. It does, however, imply they are still important, and I want to talk about ion optics a little bit. So ion optics technically take your chart species and transport it to the mass analyzer, which can be time of flight, which can be orbit trapped. The ion optic, depending on the instrument, may be configured differently. So in Waters instruments, it can be called cone and hero bias voltage. In thermal orbit trap, it can be S-lens radio frequency. It can be called something else. The idea is the same under every circumstances. Those parameters are mainly or typically biased towards masses. So higher radio frequency will be beneficial for transporting higher masses of charged species and vice versa. So you need to be aware of that, especially in the light of untargeted comprehensive applications where our goal is to detect everything we could from our sample. Now, we can have two kinds of situation. If your spectrum looks like this, so your mass peaks are evenly distributed across your acquired mass range, usually you will be good with default or average, or whatever you call it, ion optics parameters that is provided by your vendor, because you will not, or you don't want to benefit transition of either high or either small masses. However, if you deal with a spectrum that looks like this, where the majority of your peaks are shifted either into the lower or to the higher mass range, you might want to consider optimizing your ion optics. And that's what we see in this example of the urine spectrum. It's a negative mode acquired with LA reams, and we see that the majority of the peaks are in lower masses. And in our optimization experiments, we saw that the lower voltages on our ion optics really do benefit better profiling of our samples. Now, Nicolas talked a little bit about MS scan speeds in terms of data analysis or data handling, and you should absolutely consider it, because your scan rate will highly depend on the approach to data analysis that you want to have. If you want to consider just one scanning event within your peak, if you want to average, or if you want to sum. But from the terms of method development, you also need to take a look at your sample of your single generation system. And in terms of LRMs, they're usually very narrow, very small peaks of ablation event. Why don't we want to make them wider? Well, because we might want to deal with shot-to-shot variation of the laser at the first stance. On the second stance, we apply energy and we heat our samples, which will imply that over the time, certain deterioration events will take place that will affect the quality of your obtained data. And also there's a danger of cross-contamination of your samples. However, if we will talk about DIMS or direct infusion data, we can safely infuse using electrospray and ionize using electrospray samples over a prolonged time, especially if we deal with the modern configurations such as nano direct infusion or chip-based ionization sources. So over that prolonged sample signal, we can include scans of, let's say, lower speed, and we can employ mass analyzers that cannot keep up with the high scanning skip of the top of analysis, but we will gain precision in mass handling. We can also include MS2 scans within this prolonged speed without losing quality of MS1 data. So it can be something to consider at the point of data acquisition, at the point of method development. Now, further, we want to handle our data and we optimize our methods. We did acquire some sample signals, and this is the total ion current of several ablations event of pooled urine samples. So we have our sample peaks, we have our background, which is our solvent, and also the ambient, let's say, conditions within the room. They are not exactly the same. The background is a little bit bumpy, so anyone can suggest the major source of variation in this data. I will give you some spoilers. It will be the total ion current or a difference between the height within the peaks. Why does it happen? Because it's just the same sample. Those are replicates. Well, because our ablation station looks like this. It's open. It's open to ambient condition, and every fluctuation within the room will affect the amount of vapor that is transported through the sample tube. Well, the solution here may be implication of a closed environment, and those are commercially available for, let's say, imaging applications. But as Nick told before, a lot of our setups are custom built to accommodate our specific needs. And this is the recent example of NanoDaisy. So it's the Orbitrap mass spectrometer with the inlet and all sorts of custom-made appliances that are fitted to make this NanoDaisy platform happen. So sometimes we cannot change a lot into the environmental factors that influence the quality of our data, but we can normalize our data to accommodate for those fluctuations. And when we evaluate the normality of our data, when we want to take a look on how many metabolic features that we detected are repeatable across repeated measures, we calculated the coefficient of variation, and in the raw data we have 7% of features that are reliably and reproducibly detected. If we apply total ion current variation, this number rises up to 71%. But we also have the internal standard, and it's an internal standard. Intensity variation is normalization technique quite often used in LC-MS methods. When we apply it here, we don't get such good results, and I was wondering why, and I can tell you why. Because our internal standard is co-infused into within our solvent matrix that gets mixed into sample vapor at the level of the source. So when we have a high sample signal coming from the ablation station, our internal standard intensity within our co-infused matrix has a very high chance to drop, and vice versa. And this is the mismatch between your internal standards and your sample intensities that can cause the disparities upon the variation. So solution to that might be to indeed use the internal peaks for normalization or spikes within the sample that will undergo the same ablation event that will be captured within the same sample vapor and transported to the MS. Of course, there are all sorts of batch effects that can be caused by the mass shifts and that can be fixed by the log mass correction or correction or based on the internal masses. But there are also other environmental factors that you want to try to consider. One of the options is to take the signal for quality control samples. We also tried to fit linear regression on those intensities, and it doesn't work quite well with Reims data, but nonlinear regression such as locally estimated scatter growth smoothing works well for the data correction between the batches in the ambient ionization data. Now, the next thing to consider in the method development in the data normalization are your samples. So we use raw, unpretreated or minimally pretreated samples to do the analysis. And when we evaluated the reproducibility of the spectra that we get, we saw that some matrices perform better and some perform worse. And the matrices that performed worse were plasma and fishes compared to urine and saliva. And we thought, okay, urine is naturally quite low on proteins. The saliva was filtered before the analysis, so maybe the abundant mucin proteins were purified from the matrix. Plasma and fishes were used as such. So maybe the protein content plays a role in the reproducibility of our spectrum. And we did a little proof of concept analysis. So we analyzed raw urine and we analyzed raw blood plasma. And we precipitated with trichloroacetic acid the proteins in the samples and repeated the analysis. And we see that, this is the principal component analysis plot, we see that the grouping of urine samples remains quite close, so those are reproducible measurements across samples not treated for deproteinization and treated for deproteinization. Plasma, on the other hand, the reproducibility really rises when we take out the proteins from our matrix. So if you are dealing with raw, unpretreated samples, you need to be aware that there will be some variation in our data, often a quite substantial amount of variation that will be introduced by the matrix effect, by the impurities that sit in your sample. Now, those were the approaches for data generation, approaches for data normalization. We will go very quickly over applications. I have a couple of points I need to make, and then we will go for the Q&A. So as Nick said before, Reims with the soldering knife or with the electrosurgical instrument was firstly introduced to the tissue analysis. That could be within the operating room. It can also be for the online tissue, such meat quality assessment. There are a lot of applications popping up within the surgical room, and this is one of the recent publications where the authors took the Orbitrap mass spectrometer, not adapted for ambient ionization in any way, and just took it across the hospital, so passing through different rooms, passing through the corridors, exposing it to different environmental conditions. And what they saw is that the signal stays the same, the mass deviation stays the same, and it's actually applicable as such to be used in a hospital. I need to wait a little bit. And here it's back. How cool is that? Now, going back to the tissue analysis, this was a big project involving the meat quality, or specifically pork meat quality, because when you raise meal peaks, and the meal peaks are not constrained, there is a slight chance that the meat will have a very distinct unpleasant smell, and it's very difficult to measure it before you slaughter the pig for meat. And it needs to be assessed very quickly and very reliably on the slaughter line. So what we did is we actually installed the Reims installation within the slaughterhouse and sampled the carcasses as they pass through the slaughter line. So it's carcass every couple of seconds. It's a very high throughput analysis within a very unclean environments. it did allow us to quickly differentiate between different sample types. So the blanco, the samples contaminated with the smelly stuff, and and the samples that were not contaminated. We also trained the data for the classification of new samples that are coming, and we really see a very high classification rate with the false negative and false positives around 5% or less than 5%. So it's really like industrially applicable quality control measurement. We also evaluated the spectra coming from those samples, and we saw that the spectra of LMRIMs generated from meat are dominated by lipids and fatty acids. We also saw the same pattern within the specific molecules that are contributing to the separation between different meat samples. So we might think that LMRIMs is only restricted to lipid analysis, and partially it is true, because whatever ionization technique you would use, there is a certain inclination to ionize molecular species with a certain polarity. However, if we use unpretreated samples, there is also a question of the composition, of molecular composition of those samples. And that's the example of mouse brain metabolome composition. About 70% species are lipids. Lipids are usually at higher densities, and even if the technique is capable of ionizing polar compounds, the chances are high that your spectra will be dominated by lipids anyway, so just take that into account. Another food application is the huge study of fish species. The fish meat was collected from different parts of the world, I think. Yeah, I'm pretty sure. And there are a lot of fish species to detect and distinct from. We do have this huge model, and depending on the fish species, our accuracy in classification goes from 92 to 100%. So I think it's very great performance. Now, going to human samples and biofluid applications, one of our first proof of concept was within the diabetes study, when we collected fecal samples from people with normal glucose levels and people suffering from diabetes type 2. And we did a fingerprinting, and we saw that fingerprints collected from LMRIMs and UHPLC, so conventional LCMS, platform, are quite comparable within their classification performance. What we also saw is that within our detected metabolites, there is a very distinct group of features that correlates quite high with the diabetic group. And when we evaluated what can it be, it turned to be metformin as such, and metabolization products, which is the medication that gets prescribed to treat diabetes. Interestingly, we saw those metabolites both with UHPLC and LMRIMs. So despite different types of ionization, despite different pretreatment strategies, there are still some cross-linking between our ambient and our conventional platforms that we need to take care of, and especially in the strategy when you want to pre-screen your samples, ambient, and then transport to LCMS for more in-depth evaluation. We will skip that part. I will just tell you that there are a lot of nanoparticles both in LMRIMs and in paper spray ionization that can enhance the output of your data, so be aware of that. Check the recent publication. Be aware that your variability in your data comes from your sample, comes from your analytical setup and comes from the data itself, that the critical points are essential for you to understand, to be able to handle the data well. We have a lot of methods that perform really, really well outside the lab, and I think that the future of AIMS, it's my personal opinion, is indeed outside the lab for clinical and industrial applications that are still to come. I thank you for your attention, and before we move to Q&A, just a little announcement. We are hosting NUGO Week, the Congress of Nutrigenomics Society, together with Benelux Metabolomics Days. This is this September in Ghent, in Belgium. Before that, we host a postdoc course aimed at the data analysis within nutrigenomics. The program is online. It looks really good, so I encourage you to check that out. And if you'll be coming in September in Ghent, I will be happy to welcome you. Thank you for your attention. And we are going to Q&A.
Yeah, because we started a bit later, because it was early this morning, we went a bit over time, so we don't have too much time for questions left. But in any case, we would be happy to take any questions, and we can continue discussions later on as well. You can come forward maybe for a minute, Nicolas and Vera. So is there anybody that has an urgent or less urgent question for us? Please feel free. Or everybody's okay.
Okay, thank you for all the presentations. One to Nicolas. You showed the retention time, which then probably translates to acquisition time because there is no retention involved. Are they reproducible? If you have a sample and something is acquired early in the next sample, is it as early or is it later?
It's not reproducible in the sense
Use your mic.
It's not reproducible in the sense that the data acquisition is also not reproducible. The software isn't very well or acquisition software isn't very well integrated with the hardware. So it's mostly starting an acquisition on the software just to start the scanning of the instrument and then doing the sample measurement with a laser. So it's not reproducible in that sense.
More about that 5 to 10 second window where you had an ambient peak thingy, and then you had different sub-peaks in there, which might move forward and backward between samples?
It's more that due to variability of the MS instrument, it might be that the mass peak is not detected as intense as in the other peaks, but it's not that this particular compound is only detected in one scan and not in the other one, but the intensities do vary, which is why from a reproducibility perspective, it might be better to look at the entire ambient peak and quantify over that. But yeah, they're all in all of the scans, but maybe not always as intense and only during a short period of time.
Yes, go ahead.
Really set of nice talks there about ambient mass spectrometry. A couple of comments that came out during those talks are around reductions in mass accuracy or variability in mass accuracy, which got me thinking about where is it coming from. Is this down to sort of charge spacing that you get a reduction in mass accuracy, or is it just sheer number of samples that you're acquiring across and it's down to stability?
I'm itching to answer that question. I believe it's due to space charge, but the people from waters I talk to refuse to acknowledge that tough mass spectrometers can have a space charge effect because it's not arbitrary, because your space is much larger, so you don't get charged. But by sheer volume of ionized species that you simultaneously introduce into that space, I think that the space charge is or could be a major contributor in that. But also there are time shifts due to slight temperature increase in the top, which will have a huge impact into the detected masses. Ambient condition, number of samples. We do see that the type of matrix will influence the magnitude of your mass shifts that you see, because the more purer matrices, such as urine, let's say, will perform better over time, over long batches, than samples such meats or blood plasma, unpretreated blood plasma. So it's a combination. I think all of them. I do believe space charge happens, but you might hear other opinions.
Oh no, I'm convinced that space charge interactions are occurring, and I think that's happening probably in the pusher assembly just before the extraction pulse occurs. That's my thought, but I'm not brave enough to argue with Waters on that, because those guys know ion paths and stuff and all the physics behind it much better than I do.
Thank you. Congratulations for the interesting talks. And I was a little bit surprised because I think it was Nick, you presented the trimer of 3-hydroxybutyric, 3M-1, as you discussed that there's a lot of things to do to unveil for unveiling the kind of adults and compounds that can be produced in this kind of sources. Thank you.
Could you maybe specify a bit more your question? So you were surprised by the fact that there was a mass shift on the 3-hydroxybutyric acid,
It's not common at all to detect for 3-hydroxybutyric 3M-1.
Ah, you mean the ions that were formed.
Yeah. Mm-hmm.
Yeah, but okay, it's LA-Reams. I mean, it's not a common ionization source, and we do see it's something that we collaborated on with Rick Dunn as well, that there's a lot of exotic, if you can put it that way, adducts and ions formed through this combination of what happens with the laser and then the IPA, the isopropanol that is working in the source. So the fact that we see those, let's say, uncommon adducts has probably to do something with the mechanisms behind the ionization that is caused by the combination of the laser and the IPA. But it's interesting to know that it's something, do you have any?
Yeah, I was just going to say, I mean, the thing to remember with all of the ambient sources where you're not doing extensive sample cleanup and stuff is you've got more matrix in there than you'd be used to with conventional LCMS, which is why there's increased chance of exotic adduct formation and slightly different ionization mechanism taking place.
Yeah, and I think also even you will never be completely sure of the annotation, so you still need to validate, and you will have a few different options, and I'm not too sure. I mean, this was mostly demonstration data. I reviewed it back then, but I'm also not exactly sure on the conditions of analysis. Yeah, I was a bit confused now, but I think it was well covered by what Nick and Lynn said.
What is your recommendation about the mass, the lock spray, the lock mass? Because so the lock mass, should we use the lock mass over the all mass range? Because we know that the mass is not in the same range, changing in the different range of the mass. So if I use a 500 Dalton, I cannot correct 200.
Yeah, I think it's always a limit if you only have a single log mass. If you have a non-uniform mass deviation throughout your mass scale, it will be a limit to only have a single log mass. So I think if you have multiple log masses throughout the entire sphere, you'll have a better mass correction. And even then, I think there's many steps to achieve good mass reproducibility, and a single log mass will not be sufficient if your data is not very nice.
And also the intensity, if we have a low intensity, we have a different mass shifting. If we have a normal intensity of the log mass. So it's also very difficult to correct low intensity compounds in this way.
I mean, on the point of the single point lock mass correction, I have sat in Waters headquarters in Wilmslow and begged them to do a multiple point lock mass correction algorithm and to introduce the standards necessary to do that. So I completely agree with you, because the correction you're going to do at 1,000 Daltons versus 100 Daltons is going to be different, and it would be nice to have multiple points. So I really like Agilent, because they have multiple reference masses that you can use for their correction. So yeah, I completely understand your point and agree.
The solution is, what we propose is what Nicolas presented, to go to the hook point approach, where you use really the internal information that is within your own samples and the ions that are consistently present there, and you can build some sort of long-term QC to check that, as opposed to one external component, of which you don't know at what concentration to add, because as he's shown as well, you have matrix suppression issues at that point as well. I'm not a big fan of log masses anymore, if that wasn't clear yet. Yeah.
And another point, what is about the noise? Because we have matrix noise and we have noise from the machine, like electronic noise. How you split this, or you take this as a one signal to noise correction?
At this point, we don't distinguish it. It's just one noise, and we use threshold to remove it. At this point, there are some, with Nicolas, his approach, there are some distinct peaks that you pick up from all of your data, which is sort of, it's either peak you expect from biological samples or peak you don't expect and you exclude them. But for the majority part, we just remove every noise feature without distinction. Is it coming from the machine or is it coming from the matrix?
But some compounds are exactly in this noise.
They are very often unreliably detected. They have very often very high variations, so they are often not that usable.
Yeah, if you want to use, let's say, a lower noise threshold, you have to look at the CVs of those particular compounds, and if they are through the roof, it's probably not data you're going to work with in a later phase as well, aside if you get them normalized in a way that their CVs become acceptable, but chances are lower if they are in the noise region. So yeah, it's tricky. Okay, I think we will finish here to give everybody the chance to have a bit of a break before the next session starts. Thank you all for your attention. Bye-bye.